start the session. Yeah, we have started recording. Is my screen visible to everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
We started with the fundamentals. That is, we started with what is a current. Before that, what is basically a charge. Flow of charge is nothing but at what speed is nothing but a current. And then to make this charge move, we need some external pressure or some energy, which is nothing but the voltage. Okay, so voltage can be generated using battery or generator. Okay, so that is represented normally when you draw a circuit. So the external excitation or the okay. So now we have two more terms. One is power, the other. Now, other than this, we have the important circuit elements called resistance. That is, basically there are two categories. One is active element, the other one is a passive element. Okay, so as discussed already, so the element which are able to generate energy, they fall under the category of active element. Okay, so yeah, active element. So now the elements or the components which are going to consume energy or absorb the energy, they are called as passive elements. So basically there are three passive elements as mentioned already. So we are going to start with the DC circuits. What is DC circuits? That is the circuit which is going to have a constant voltage source, direct current, constant or voltage source or a constant current source. Okay, so now here we are going to consider the circuits consisting of only resistors. Okay, because the capacitors and inductors, when you consider, when there is a change in current or change in voltage, then only there is going to be a EMF induced or current flow. Okay, that is your source should be a what to say, change in voltage or change in current. It should be something like this. Okay, or something like this, which is going to vary with respect to time. Okay, if you have a constant quantity, constant voltage or constant current applied to this inductor and capacitor, there won't be any effect. Okay, we will discuss that in detail in the next module. Okay, so now we are going to consider the DC circuits comprising only resistance. Okay, as discussed already, so any circuit you consider, even though you apply some pressure as a source, even though you have a source. Now, if I connect the load here, I represent a bulb load like this. Okay, so now there is going to be some opposing force. There is going to be some opposing force. So this opposing force is represented like a resistance. Okay, so depending on this opposing force, depending on this. Sorry. Somebody is interrupting me. Any doubt? I'm not able to hear. Okay, fine. Okay, so now the amount of opposition is nothing but the resistance. If higher the opposition, lower the current flow. So the resistance, higher the opposition, resistance will be higher and the current flow will be lower. Okay, so depending on the material, for example, when you consider the metal or aluminum, which falls under the category of conductors, okay, so they have very good conductivity, more number of free electrons. So the resistance offered by these elements are very minimum. Okay, that's what when you consider this copper wire, simple copper wire is a very good conductor. So ideally speaking, they don't have any resistance. There is going to be a maximum current flowing through this. Okay, so the resistance, ideally we say that 0 ohms. Ideally we say that 0 ohms, but practically some minimum amount of resistance is there. Okay, similarly, when you consider the insulator, like silicon dioxide, okay, so or air. So when you consider an insulator like this, you have the what to say, maximum opposition. There is no free electrons, there is no possibility of current flow in that. So the resistance offered by those kind of materials are infinite. Semiconductor will have a midway. Okay, so this is how the resistance. Now, as discussed already, the resistance is depending on all these parameters. Okay, so the temperature also plays a major role. How is it going to affect the resistance? The resistivity of the material. The resistivity of the material is going to be different. For example, I can consider a conductor. I can consider a conductor. Okay, so aluminum or whatever. Metal or even polysilicon. They are all very good conductors, right? So now I consider this conductor. This is a representation. I'm considering a conductor. So here I have so many atoms with a number of free electrons. Okay, so when I have this conductor with external pressure or external energy, so now if this is operated in the normal room temperature 27 degrees centigrade, then there is going to be a maximum current flow. Okay, so now if this temperature is increased, okay, so now what is expected to happen? Because of this increase in the temperature, what is going to happen? See, the atoms, they will, because of thermal energy, other than this, these atoms are getting the thermal energy, that is increase in temperature. So they will try to move faster. So because of this movement, what will happen? The atoms nearby, they will collide each other, which is going to further reduce the rate of movement. Let me repeat. So already we have some external electrical energy supplied to this material. So because of which there is going to be a movement of electrons. Okay, so which is going to, there is a current flow. Now let us assume that this is operated in the room temperature. Okay, so if suppose the temperature, the operating temperature increases. So what happens? Due to the increase in the temperature, the thermal energy applied to this material also increases, due to which the atoms move fastly. So what happens? They try to hit the nearby atom. Okay, so because of this collision, so what is expected to happen? The effective net transfer of electrons reduced. So this is nothing but negative temperature coefficient. So the conductors, they have the negative temperature coefficient. What is the meaning of negative temperature coefficient? As the temperature increases, the current flow in the material decreases. Okay. Similarly, when you consider the semiconductor is having a, unlike a conductor, this is having a normal conductivity. So in this case, for semiconductor material, like your silicon or germanium, those two are the popular two semiconductors, right? So for this semiconductor, the temperature coefficient is positive. Okay, so because of this thermal energy, the number of electrons, free electrons increases. Okay, already due to the diffusion, the semiconductors will have some free electrons. Now, since the temperature, operating temperature increases, the material acquires some thermal energy. So the number of free electrons increases. So the current flow increases. Okay. So for semiconductor, we have a positive temperature coefficient. What is the meaning? As the temperature increases, your current flow is also increasing. Okay, so that's what is the rho. That's what is the rho. So even though in this equation we don't have a direct temperature element, so indirectly the resistivity of the material temperature. Okay. So now these are all the different types of resistors. Okay, so only two things I wanted to mention here. So this is these are all the normal resistors which we they are all called as carbon film resistance. Okay, so and then we have another important thing. You're all computer science students, you may not be using it, whereas the electrical engineers, they use this wire wound resistors. The difference between this carbon composition resistor and wire wound resistor is these kind of resistors, they can be used, that is the maximum power handling capacity or the output power handled by these kind of carbon composition resistor is maximum of 2 watts. That is the current the maximum current that can be handled by these kind of resistors are very minimum compared to the wire wound resistors. Okay, so wire wound resistors, they can handle the current in the range of amps, 2 amps, 4, 5 amps. Motor, no, they will be connecting the motor load Okay, whereas these kind of resistors are used for the simple electronic circuits, like a simple 10-volt motor when I want to use in the robo, or simple lightings, LEDs I want to use in my house for some decoration purpose. For those kind of things, the simple resistors, which can handle the current in the range of milliamps or microamps. Okay, so the maximum power is only. What is the difference between these two things? Other than that, we have two more important category. One is fixed resistor. All these are having fixed resistance. I do not know whether you have learnt in your 11th, 12th. Okay, so depending on the color coding, the value of the resistance can be determined. So it's having a fixed constant resistance, 100 ohms or 1 mega ohms or 10 kilo ohms, whereas this is a variable resistor. Okay, so people used to say 10K pot. Okay, so the resistance of this can be varied. So these two are the fixed ends, and this is the variable end. By you have this knob, no? By adjusting this knob, the resistance of this potentiometer can be, potential divider can be adjusted. Can be adjusted. These are also something like a resistor only, because this is basically these are all sensors. In your robotic application and all, you might have used the sensors, right? Thermistor, LDR, these varistor, all these are the sensors. That is depending on the they accept the input. What kind of input? Temperature input. Depending on the temperature, the resistance of the sensor thermistor will vary. Okay, so as the temperature of the I have the sensor, I light a matchbox. Okay, when I apply that temperature to this thermistor, resistance output of this, you measure the output of this thermistor as a will have the variation. Thermistor has a negative temperature coefficient. Okay, similarly, this LDR, light dependent resistor. So this has a light input. That is, you can have your normal bulb, your LED input, or any or sunlight, any input. Depending on the light input, the output resistance of this can be varied. Okay, they are all non-linear resistors. Okay, so these are all the different. Okay, then already yes.
Remember to all those type of.
I'm not audible, ma. Can you say a little louder?
Hello, am I audible, ma'am? Hello. Hello.
Now it's audible. Now it's audible. Tell me.
Yeah, ma'am. Is it essential to remember all those types of resistors?
No. Just you have just as an information. I'm just telling you.
Right.
Mostly we'll be dealing with analysis of circuits only, but just I'm what to say. Just an information I'm conveying. Okay. So now this is Ohm's law. So we discussed already. So generally for any circuit, we have a source and we have the load. Okay. So now the current flowing through the circuit is proportional to the applied voltage at a constant temperature. Okay. So now this constant of proportionality is nothing but resistance. The resistance of this material is going to give some opposition. So now if this resistance is constant, then we have the uniform current flow depending on the applied voltage. Okay, so if this resistance is varying, so why you have a possibility of varying resistance? Because of the temperature. Okay, that's what we have mentioned. At a constant temperature, as per the Ohm's law, the current flow in any circuit is proportional to the applied voltage. Now, power and energy. So as already mentioned, discussed, so power is nothing but it is an indication of what is the amount of work done per unit time. Okay, so now based on this, we have the energy also. So energy is nothing but just power into time. Okay, so what is the amount of work done? Okay, so now here the electric heaters and light bulbs. Okay, all these are the examples of the resistive load. So most of the loads available in our households are resistive loads, either resistive load or inductive load. Okay, that is whichever load is giving the heat energy as an output. Okay, bulb will give the heat energy. Okay, your iron box, your bread toaster, what else? So all these are the different examples of the resistive loads. Okay, so wherever you have the magnetic coil, that is wherever you have a motor, your fan, your washing machine motor, refrigerator motor. All these are the examples of the inductive loads. Whereas your capacitive load is very, it's normally very minimally used load. Okay, so now here the power of the loads are represented by watts. Okay, that is okay. So higher the watt rating, the more energy we can get out of it. Okay, that is higher rating motor can have maximum output. That way it is. Okay, so power is nothing but work done per unit time. Now, for an electric circuit, how do we find out this power? For an electric circuit, how do we determine this power? Okay, so as discussed already, your voltage is nothing but what is the amount of work done? That is, what is the, this can be represented in two different ways. So your power is nothing but work done. Okay, so which is nothing but work done by Q multiplied by Q by 2. So we can rewrite this expression like this. So this is what is the amount of what is the energy applied so that there is this much of, how do we define this voltage or potential difference? For this much of potential energy applied, we have this much of movement of the charge carriers. Okay, so the voltage can be defined as W by Q. So now here the power in an electric circuit can be expressed as V into I. So we know that the rate of movement of charge carrier is nothing but I. Q by T is I. And then what is the energy required to move the charge? Okay, so now that is nothing but the voltage. What is the potential energy required to move the charge carrier? W by Q is nothing but the voltage. So now power is nothing but V into I. Okay, so now if we apply the Ohm's law, as per the Ohm's law, I can be written as V by R. So now power can also be computed with the expression V square by R. Same way, the V can also be replaced as I into R. So now the power expression can also be represented as I square R. The unit of power is watts or joules per second. Okay. Power rating of resistors. Okay, as I mentioned already, wire wound resistor, carbon film resistor. Okay, what is the amount of current that can flow through the resistor? There's nothing but the power rating. What is the maximum current that can be acceptable by the resistor? So you can ask me, mom, if the current exceeds beyond the maximum, what will happen? The resistance will melt. The resistance will melt. Okay, so it cannot handle, so it will be blown. Okay, so that's what, when we handle the resistors with minimum power rating, 2 watts, 3 watts, normally what we do simple circuits, right? 10 volt motor or simple LED connection or some demo projects. Okay, so in those cases, there is no issue. It's it's absolutely harmless. Whereas when we handle the resistors with high rheostats, I mentioned, wire wound rheostats, which is going to handle the current in the range of amps, okay, kilowatts. Okay, so those rheostats are really, we have to be very careful when you use those kind of rheostats. Okay, if there is any open circuit or if there is any maximum current, then it will blow off. It will create a damage to the people. So now energy. Okay, so now amount of energy or amount of work done per time, unit time is a power. So from that we can derive what is energy. Okay, energy is nothing but work done per unit time. It's nothing but power. So now work done is nothing but energy spent. Okay, so now energy can also be represented as P into T. So now it is measured in normally in seconds. So the energy is watt seconds. Okay, so watt seconds or watt hour, kilowatt hour. Okay, so all these are the representation of what is the energy consumed by our household appliances. The light is consuming the energy 1 watt hour. My fan is consuming the energy of 2 watt hour. Okay, or another washing machine consumes maybe 10 watt hour or kilowatt hour. So now the total energy consumed by all the loads will be the sum of the energy consumed by the individual loads. Okay, so now let's move on to the yes.
Ma'am, is work and energy the same quantity, ma'am?
Yes, correct. That's what the amount of work done is nothing but energy spent. Work done is nothing but energy spent. What is the
Yeah.
work done and what is the energy spent is same. Okay, that's what I was trying to say. W by Q, energy spent to move the charge carrier, or work done to move the charge carrier. Okay, so W by Q. W is nothing but energy. Okay, so here we are going to consider the circuits. Okay, so here when you consider, simply we have considered a circuit, we have source, we have a load. Through the switch it is connected. Through the switch it's connected. Now we are going to have a possible circuits. One is a series circuit, the other one is a parallel circuit. Okay, so what is series circuits? So like this, we have a circuit consisting of more than one element. You have so many elements connected in series. Okay, so what is the example for the series circuits? You can see during Christmas or any function, people used to connect so many LEDs, right? So many LEDs, and the LEDs will be supplied through the switch to the supplied by the battery, or supplied by the battery through the switches, right? So now you have so many LEDs connected, right? So that is a good example of series circuits. That is a good example of series circuits. Similarly, when you consider microwave oven, there are inside the oven, if you see, there are too many number of sensors. There are too many number of sensors, which is nothing but too many number of switches. Now all these switches are connected in series. Okay, so those are all the kind of examples for the series circuits. Okay, so now series circuits. What is series circuits? A circuit consisting of many number of elements joined at a terminal. Okay, providing a closed path. See, this is the closed path. That is my pen. Yeah, this is my closed path. See, here the rule is two elements are in series when they have the common point between two elements. For example, here this is a common point between these two elements. Here we have a common point between these two elements. Okay, and then they have only one terminal in common. They have only one terminal in common. For example, here I have this common point. Okay, I have this common point between the two elements. If suppose I have the third element here, if suppose I have a third element here, then definitely this is not a series circuit, because at this junction we are going to have a split in the current. Current will split here. So definitely this is not the series circuit. Okay, so what is the series circuit? They have only one terminal in common, and then the elements are connected in series. Okay, so now what are the properties of the series circuit? So this is forming a closed path. So we have the same current. Okay, so whatever is the current, so this is going to provide some opposition. So the opposition or the current flow in the circuit depends on the total resistance. Okay, I have so many resistors connected in series. So the total resistance, depending on the total resistance, the amount of current flow in the circuit is going to be. Okay, so now whatever may be, if suppose 2 amps or 2 milliamps is the current, then since this is a same loop, there is no path, or there is no point where the current is going to divide. So whatever is the current here, the same current is going to flow in this complete circuit. Okay, so the current is same in the series circuit. Okay, and then the total resistance of the circuit is sum of the resistances. Okay, so here how do I determine what is the current flow? We have to find out what is the total resistance of the circuit. So what is the total resistance of the series circuit? Sum of the resistances. Okay, so here the total resistance is R1 plus R2. Okay, and then what is the current? Current will be, as per the Ohm's law, current will be V by R. Okay, so V here V is nothing but source, which is represented with the term that is E, which is represented with the letter E. So E by the total resistance, RT. And what is the unit of current? Amps. So the current flowing through the circuit is going to be E by RT. What is RT? Where RT is R1 plus R2. Okay. So now here for series circuits, what could be the power and how do we determine the energy? Okay, all these things. So as discussed, your current is this visible? Is this visible?
Yes, ma'am.
All the
Yes,
fonts
ma'am.
are visible?
Yes,
Okay.
ma'am.
Yes,
Okay,
ma'am.
good. Okay, so now as discussed, so the total resistance is R1 plus R2. So the current is E by RT. Okay, now here we have another interesting thing. For example, okay, so let us consider this circuit. Okay, now the question is, if suppose this has the resistance of 2 ohms. Okay, this resistance has a value of 10 ohms. Now the question is, if I measure the potential difference between, for example, let us name it as A, B, C. Okay, so I'm trying to measure the potential difference between A and B. I write it as VAB. Now I measure the potential difference between B and C. I write it as VBC. So now I have a question to you. Will these two, VAB and VBC, will it be equal or not equal?
Not equal.
Not equal.
Why it is not
Not
equal?
equal.
Why it is not equal?
Resistance varies.
So because of the resistance variation, for example, this is going to give some energy. This is going to give some energy. Okay, so now because of this energy, there is going to be a current flow. Okay, because of this current flow, there is some work done. Okay, so now obviously, so the potential difference between these two is going to be, okay, that is the amount of work done for this is going to be definitely different than this, because the charge, the number of charge carriers which is going to cross from here to here and here to here, when you see, definitely this has a minimum resistance, no? So the more charge carriers or more current, that is what to say. So here the work done is going to be more. Okay, so now definitely in series circuits, the potential difference or the voltage drop across the resistors will not be equal. It will be different. So what is the concept here? In series circuits, you have the same current, but the potential drops across the resistors will be different. Okay, so now here the total voltage E is divided between these two resistors. The total voltage is divided between these two resistors. So now I into R1 plus I into R2 will be equal to I into total resistance RT. Okay, so now how do I determine the power dissipation? How do I determine the power dissipation? Okay, so already we have the expression I square R or V square by R. So now so the power can be determined. Power dissipation across, it's not the total one can be the what is the power dissipated or power dissipated across 2 ohm resistor, and what is the power dissipated across this 10 ohm resistor. Or we can say that what is the total power supplied by the source? What is the total power supplied by the source? So total power supplied by the source is going to be E square into the total resistance. Sorry, E square by the total resistance. Okay. Whereas the power dissipated by this individual resistor is going to be whatever is the voltage drop across this. It's going to be VAB. So VAB square divided by R1. So this is going to be VB square by R2. Now again here, if you recollect, there is going to be power supply and power absorption. So now power supplied by the source will be equal to the power absorbed by these two loads. Okay, so now total power PT will be equal to P1 plus P2. What is P1? Power dissipated across this resistor, and P2 is the power dissipated across another resistor. Okay, so now here we can calculate the energy also. So after I find the power, multiply it by, after we find the power, we can calculate this. Okay, so now I have an example for you. I have an example for you. So here there is a question. So here we have the circuit, which is having a DC source of 20 volt. Okay, and then 3 resistors are connected. So definitely this is a series circuit. This is a series circuit which forms a closed loop, and there is only one terminal between any two elements. There is only one common terminal between any two elements. So this is a series circuit. Now the question is, calculate the source current. Calculate the source current. So this is nothing but the source current. Current supplied by the source. So how do we determine the source current? How do we determine the source current? Voltage divided by the total resistance. resistance. Voltage divided by the total resistance. Now, what is the total resistance? What is the total resistance? This is a series circuit. So total resistance will be summation of the resistance. Very good. So it's going to be 5 plus 1 plus 2. So it is 8 ohms. Okay. So now I is nothing but voltage source is 20 volt and the total resistance is 8 ohms. So we have 2.5. Am I right? So 2.5.
Yes, ma'am.
So very good. So now the source current is 2.5 amps. So what is the next question? Determine the voltage is V1, V2, V3. So you can compute it. So what is V1? V1 is nothing but current flowing, voltage across the R1 resistor, voltage drop across the R1 resistor. So we can find it I into R1. Okay. What is I? I is nothing but 2.5. So 2.5 into 2 ohms, 5 volt. Then V2 is voltage drop across the resistor R2, which is 1 ohms into 2.5 amps. So it's 2.5 volt. And then V3 is same way, 5 ohms into 2.5. So 7.5. So when you sum all these things, V1 plus V2 plus V3, that is equal to the total voltage, source voltage. Okay, now another question.
Hello, ma'am. This V3 is
12.5. 12.5.
12.5. Okay, I think I did a mistake, right? So 5 into 2.5 is, yeah, correct. 12.5. Sorry, correct.
Ma'am,
So 12.5.
Ma'am, actually, is E same as the voltage, ma'am, or is E equal to EMF, ma'am?
No. Actually speaking, we can use these two terms. We can interchange these two terms, but here generally this is nothing but the voltage source. Here this is nothing but the voltage source. Electric field, electromotive force, voltage drop, potential difference, voltage rise, voltage. All these are same. Okay, but here let us not confuse. This is a voltage source V or E. So in different books, they use different notations. This is a voltage source, which is going to supply energy to this circuit. Okay,
Yes.
so this can be a battery, generally battery or RPS, regulated power supply. Okay, so now the third question is calculate the power dissipated or dissipated by R1, R2 and R3. So you can calculate, right? I1 square R1, I square R1, I square R2, I square R3. Okay, and then or otherwise you have V1, V2, V3, no? So V1 square by R1, V2 square by R2, V3 square by R3. And then determine the power delivered by the source. Okay, so power delivered by the source is equal to total current square multiplied by total resistance. So 2.5 square multiplied by total resistance is 8. Okay, so I guess 6.25 into 8. Okay, so you can do this. So you can calculate this using your calculator, or those can do quicker without calculator can tell me the answer. 8 into 6.25 watts.
50.
50 watt.
Sorry?
50 watts, ma'am.
50.
50 watts.
50 watts.
So 50 watts. Now when you calculate the power P1, P2, P3, and if you sum P1, P2, P3, that should also be equal to 50 watts. Okay. We have another circuit. So now here, given total resistance, calculate R1 and E. So you're asked to compute what is this resistance and what is the total voltage. What is the voltage source value? And you are given with the total resistance. Okay, so RT is given. So we know that this is a series circuit. So total resistance will be R1 plus R2 is 4K and R3 is 6K. Okay, so now from this I can find out what is R1. What is R1? Total resistance is 12K. So 12 minus 4 minus 6. So it's 2K. Okay, so 2K, and then how do I determine what is the power? Sorry, what is the E? How do I determine what is the E? The current is given here. The current value is given 6 milliamps. So I is equal to E by RT. Okay, So current is given as 6 milliamps and your voltage value can be determined from this. So into total resistance is 12 kilo ohms, right? So 12 kilo ohms, which is nothing but E. Okay, so 12 into 6, 72. So
72.
10 power minus 3, 10 power plus 3 will get cancelled. So E is 72 volts. Okay, and then already, I think in yesterday's class, I asked you this question. People are able to answer me. So when you have voltage sources in series, they will also be getting added here. So can anyone tell me the expression for ET, the total voltage E? Oh, I think they've given the values. So this is 4 volt and this is 9 volt and 3 volt. So here we cannot just like that add like 4 plus 9 plus 3. We have to consider the polarity of the voltage sources. Okay, so here, how do I represent here? This is represented as plus minus. So here, this is 9 volt, which is plus minus, and here we have 3 volt plus minus, and this is minus plus. Okay, so definitely this voltage is opposite to that of this. So I can say that E2 plus E3 minus E1. You can ask me, ma'am, why you are writing E2 plus E3 minus E1? Why not E1 minus E2 minus E3? Okay, because this
Opposite.
plus minus and this plus minus is same. Or otherwise, I can find out the value. For example, here 9 plus 3, 12, 12 minus 4, 8. Okay, so if suppose this is also like this. Say suppose this is 4 volt and this is 3 volt and this is 2 volt. So now can anyone tell me what will be the net voltage? Will be a negative value or positive value? Should I represent plus minus or minus plus?
Positive value.
Ma'am, 3 volt.
That's one. Here this is 3 volt, which is plus minus. Okay, whereas here this is minus plus. This is also minus plus. Okay,
Minus 3
so
volt.
these two can be added. So 4 plus 2, 6. 6 minus 3, 3. Okay,
3 volt.
so now this 3 should be represented with minus
Minus
plus or
3. Minus.
minus 3. Yes,
Yes, ma'am,
so
minus
minus 3. Minus 3 is the answer. So this way we will have the circuit. Okay, voltage law, Kirchhoff's voltage law. Okay, so fine. Maybe I will stop with this Kirchhoff's voltage law. Just I will say what is the law here. Okay, so now we have, so far we have discussed the series circuits. Now what is the point we have discussed? So now here we have the voltage source. We have the voltage source here, and then this is going to supply some current to the circuit. So the total current or the current supply to this is going to be same. Throughout the circuit, it is going to be same. So because of which we have the voltage drop across these two elements. So now the statement as per the Kirchhoff's, as per the scientist Kirchhoff, he found that the total voltage in any closed loop, is equal to 0. Here, let us consider, as discussed already, so the voltage drop across these two will be equal to the total voltage supplied by this. Okay, so obviously it follows that statement, no? So the voltage, yes, as per the KVL, the algebraic sum of the total voltage, algebraic sum of the voltages in a closed loop is equal to 0. Okay, so now for analysis purpose, we are going to discuss so many circuits for analyzing, right? So now for analysis circuits, let us remember that always in a closed loop, the current can be represented either in a clockwise direction or in a anti-clockwise direction. Okay, now let us do like this. For any circuit, we are going to follow only clockwise. For any circuit, we are going to consider the current direction in clockwise. Okay, and then one more thing is, so we are going to now, from now onwards, we are going to say voltage rise and voltage drop, potential rise or potential drop. So now we will say potential rise as positive and potential drop as minus. Okay, so that is, we will represent the voltage. No, the voltage can be, we have the polarity for the voltage, right? Depending on the current flow, right? So now the voltage rise is represented as plus V and voltage drop is going to be represented as minus V. You can have any notation, but we are going to keep this We are going to have this reference and we are going to follow this throughout the analysis, throughout this module 1, or throughout the module 1 and module 2. Okay, so always we try to assume the current direction in clockwise, and we are going to assume the positive polarity for the voltage rise and negative polarity for the voltage drop. Okay, now what is this voltage rise and voltage drop? Okay, so now I have the current flow, right? I have the current flow. So always the current will flow from higher potential to the lower potential. Always the current flow from the higher potential to the lower potential. Okay, so now this is, see, when I say the current direction like this, then obviously it's going to be higher potential represented as plus, lower potential represented as minus. So now this is drop. Okay, now here when you consider my current direction is like this, my current is flowing from minus to plus. So it's going from lower potential to the higher potential. This is nothing but rise. Okay, so let me repeat. We are going to, that is as per the Kirchhoff's voltage law, the sum of the voltage in a closed loop is 0. Now we have three things. One is a current flow. Always let us consider the current flow. Initially, we are going to assume some current direction. Then after the analysis, we find the value. If the current value, what we find is positive, then our assumption is correct. Okay, so now if suppose your answer, the current value what you are getting is negative, then what does that mean? Our assumption is wrong. Your original current is opposite to that of the assumed current. So now we are going to assume the current flow in clockwise direction. I think I made my point clear. Now, based on this, we have voltages. Voltage can be rise. What is rise? When the current flows from lower potential to the higher potential. That is nothing but rise. Okay, then when you have the current flow from higher potential to the lower potential, that is a drop. So we have the voltage rise and voltage drop, and let us try to have plus for the voltage rise and minus for the voltage drop. Okay, so now these are all the equations. So now sum of the voltages in a closed loop is 0. So from that we can say that voltage rise in a circuit is equal to voltage drop. Sum of the voltage rises in a closed path is equal to sum of the voltage drops in a circuit. Okay, so with this, we have some circuits to be solved. Maybe let us continue this in the next class. Okay, so any doubts so far? Any doubts so far based on
Ma'am,
this?
actually, can you explain that positive current and negative current only once, ma'am, the last slide?
What did I mention is, see here in the circuit, when I want to analyze the circuit, I will assume some current, right? Okay, so initially we do not know whether the current is going to flow like this or this. So what do I do? For the analysis purpose, for the calculation purpose, what I do, I have a circuit like this. So I assume the current direction like this, clockwise direction. Okay, like this. Then after the calculation, after I analyze the circuit, I find the current I is equal to, what is the value we are getting? 6 plus 4, 10. So 20 by 10 is 10 amps. So we are getting a plus 10 amps. Okay, so now my assumed current direction, since my current is plus 10 amps, my assumed current direction is correct. The original current flows like this only. Okay, if suppose instead of, if this is the source and I assume the current direction like this, then what will be the value I'll be getting? I'll be getting minus 10 amps. So what is this? What is the indication of this? My assumed current direction is opposite to that of the original current direction. My original current is like this. That's what I was saying. Am I clear now?
Thank you, ma'am.
Okay, good. Any doubt for
Excuse me,
anybody?
ma'am. Ma'am,
Yeah, tell me.
Can you please upload this PPT in the file section?
Sure. After I finish this